These are going to be our notes for limits at infinity. So one of the things that we are often interested in when we're looking at a graph is the behavior of this graph on its ends. And what we mean by that is far out to the left and far out to the right. And what we know is that when you're looking at the far left or far right of a graph, to the far right we know that that means that x is extremely positively large, and to the far left we know that that means that x is extremely negatively large. So what we look at is the limit as x approaches infinity, meaning x increases without bound on the function. And we take that limit and we say it's equal to L, and that's our end behavior on the right. Or the limit as x approaches negative infinity, meaning it increases without bound but in a negative direction. That's our end behavior on the left. Now the result will sometimes be an infinite value, other times it will be a finite value, but those are not the only possibilities. It could also not exist at all. But when we take that limit as x approaches infinity, it tells you what your graph does on the right. And when you take the limit as x approaches negative infinity, it tells you what your graph does on the left. If you happen to get a finite value when you take a look at this limit, what you're actually looking at is the horizontal asymptote of your particular graph. So we say that the line y equals L is a horizontal asymptote of the graph f if, when you take the limit as x approaches infinity on the function, you get some kind of number L, that line y equals L, or as you take the limit as x approaches negative infinity on f of x, you get L. In both cases, what you're going to pick up is the horizontal asymptote. Now that is, again, assuming you get a finite value. So for example, if we take a look at f of x equals 3x squared over x squared plus 1. Now this is one that we have examined before in, let's say, a pre-calculus class. And normally in pre-calc what we tell you is that if you want to find the horizontal asymptote of a rational function, which is what this is, you would compare the degree of the numerator to the denominator. Notice they have the same degree, in which case we expect their horizontal asymptote to occur at the ratio of the leading coefficient. So that's 3 over 1. Sure enough, if you look at the graph of this particular function, you definitely get a horizontal asymptote at 3. Now that we're in calculus, what we're saying about this, though, is that the limit as x approaches infinity on 3x squared over x squared plus 1 is equal to 3. And in this case, the limit as x approaches negative infinity on 3x squared over x squared plus 1 is also equal to 3. When you're dealing with rational functions, you tend to get the same number on the left and the right. Now, that will not be true for all functions. There is the possibility that you have a different horizontal asymptote as x approaches infinity compared to when it approaches negative infinity. So that is one way we use these limits as x approaches infinity. Let's take a look at some techniques for actually finding the limits, for calculating them. It's one thing to look at a graph and say what is the limit, but we need to be able to do this using other techniques. So let's find the limit as x approaches infinity of 1 minus 1 over x. So one of the things that we can do is we can use the property of limits that says you can split limits across addition and subtraction. So we can look at the limit as x approaches infinity on 1 minus the limit as x approaches infinity on 1 over x. And a lot of the limit laws apply. The limit as x approaches infinity of a constant is the constant. That's true for all limits. Now, what's going to change up just a little bit is the second part of this. When we talk about the limit as x approaches infinity of 1 over x, direct substitution isn't technically an option for this. I mean, you can't plug in infinity because it's not a number. It's not something that you can calculate. But you can use the conceptual idea of this, meaning you're letting x grow without bound. And what you have is 1 divided by something that's getting infinitely large. And think about what that would look like if we just looked at some numbers. So let's say that's 1 over 10 compared to 1 over 100 compared to 1 over 1 million. If the denominator is getting infinitely large and the numerator is that constant, what's happening to the fraction overall? Well, overall, this is approaching 0. It doesn't ever get there, but it approaches 0. Remember, limits are about what happened near infinity. Obviously, we can't actually equal infinity. So when we look at this, what this limit should end up being is 1. So to kind of put that into verbiage, a constant divided by a value that's getting infinitely large or infinitely negatively large will get infinitely small, meaning it will approach 0. So for example, if we had looked at, let's say, the limit as x approached negative infinity on the same function, 1 over x. It wouldn't matter that this was increasing without bound in a negative manner. It would still be the same exact concept, only you'd have 1 over negative 10, 1 over negative 100, 1 over negative 1,000,000. They are still approaching the same value. It's still approaching 0. So that's actually a really important concept that's going to help us when we look at more complicated limits as x approaches infinity or x approaches negative infinity. For example, let's find the limit as x approaches infinity on 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1. If we try to, I hesitate to call it directly substitute because technically you're not substituting infinity, but if we follow the concept of letting x get infinitely large. In the numerator, you see that we have a quadratic, and as x approaches infinity, quadratics approach infinity. So the numerator is going to get infinitely large. The denominator is also a quadratic, and as x gets infinitely large, so does the quadratic. Well, so what we end up with is infinity divided by infinity, and that is what we refer to as an indeterminate form. And recall, indeterminate form means I literally don't know what the answer is going to be. The tendency is to want to say that infinity divided by infinity is 1. And that's not necessarily going to be true. In order for you to assume that infinity divided by infinity is 1, those infinities have to be the same, and that's not necessarily going to be true. So when we get this form, we don't know what the answer is going to be. It might be 1, it might be infinity, it might be negative 1/3. We have no idea. It's going to depend on our function. We're going to need to make it look different than it currently looks before we're going to be able to determine the result of taking the limit as x approaches infinity. So, we've done this before. I mean, when we looked at things like, the limit as x approached 1 on x squared minus 1 over x minus 1. This was not something you could directly substitute 1 into as is until you rewrote it. You factored the numerator to x plus 1 times x minus 1 and canceled the x minus 1s. And this ended up being the limit as x approached 1 is x plus 1. And then you were able to directly substitute. So the idea is you need to alter what your current limit looks like. So the technique, when you're looking at infinite limits and you have a rational function, one of the things that you can do is to divide the numerator and the denominator by the highest powered x in your denominator. Well, in this case, the highest powered x in my denominator is x squared. So as long as we divide both the numerator and the denominator by x squared, it's going to be equivalent algebraically. Let's take a look at what that looks like. When we divide both numerator and denominator by x squared, remember, this x squared is going to be able to divide into every term in the numerator, as is this one. When we do that, the x squareds in both of the first terms will cancel. I'll be left with a 3 in the numerator and a 5 in the denominator. Here I'll get 1 over x. Here, 2 over x squared. Here I'll get 4 over x. And here we'll get 1 over x squared. Also remember, by properties of limits, the limit of a quotient is the limit of the numerator divided by the limit of the denominator, assuming we don't end up with a 0 down in that denominator. So when we split that up, and then we're able to split it again across addition and subtraction, we'll have the limit as x approaches infinity on 3 minus the limit as x approaches infinity on 1 over x minus the limit as x approaches infinity on 2 over x squared. And again, we'll be able to do the exact same thing down here. I won't write them all down because you get the idea, I think, at this point. You can keep going, etc. And then we can take each limit individually. We'll notice in the numerator, the first one is the limit of a constant. We know what that's going to be. That's going to be 3. But take a look at the second and the third terms. You're taking the limit as x approaches infinity of 1 over x, and didn't we just say that as long as you have a constant up in your numerator, if your denominator is getting infinitely large, this is automatically going to go to 0. Notice in the third term, we also have a constant in the numerator, and this time it's an x squared in the denominator, but it's still going to get infinitely large. This is also going to go to 0. So every one of these fractions that still has a constant in the numerator and a variable in the denominator, as that variable goes to infinity, those all go to 0. So this limit actually ends up being equal to 3/5. If we were to repeat this process as x approached negative infinity, we would also get 3/5 as the limit, because remember, it doesn't matter whether it's going to positive or negative infinity. If it's a constant in the numerator, it's going to trend towards 0. So if we take a look at the graph of f of x equals 3x squared minus x minus 2 over 5x squared plus 4x plus 1, this is what the graph looks like. And sure enough, this is the line y equals 3/5 is 0.6. And as x approaches positive infinity, this is going to go towards 3/5. And as x approaches negative infinity, this is going to go towards 3/5. Also notice, that's the horizontal asymptote for this particular function. Let's take a look at another example, but before we do, I want to ask you this question. True or false, the square root of x squared is equal to x? And the answer, believe it or not, is actually false. Okay? We're very used to, hey, if you have a square root and a square, they're going to undo each other and just leave you with your x. I mean, it is true that something like, I don't know, the square root of 1,172 squared. Yeah, it's 1,172. The square and the square root undo each other. So why is this a false statement? Well, because it depends on what number you're looking at. I mean, let me make it a little bit smaller. The square root of 5 squared. If you don't just cancel the square and the square root, meaning you actually square the 5 to get 25 and then take the square root, you're absolutely going to get 5 back. So I still haven't shown you a reason why this wouldn't be true. Try this one. What's the square root of negative 5 squared? If you square the negative 5, you get positive 25, and when you square root that, you come back to 5. Is your input the same as what you outputted? And the answer is no. Now, what was the difference between the negative 5 compared to the other two examples? Well, it's negative. So it turns out that the square root of x squared is actually equal to one of two things. Sometimes the square root of x squared will be equal to x. If your input was positive to begin with, then you're going to get that input directly back out. So by positive, we mean greater than or equal to 0. However, if your input is negative, as it was when we put in negative 5, you don't get back the same number that you put in. What you get back is the opposite of that number. In this case, it'll be the positive version of that number. So in other words, you get the opposite of x. So sometimes the square root of x squared is equal to x, and sometimes it's equal to the opposite of x. We're going to use that idea in our next example. By the way, this definition should look awfully familiar. Turns out it's the absolute value of x. So the square root of x squared isn't equal to x, it's equal to the absolute value of x. So let's take a look at this one. We're going to find the horizontal asymptotes for f of x equals the square root of x squared, 2x squared plus 1 over 3x minus 5. Okay? So notice the change in directions. The directions no longer say find the limit as x approaches infinity. It says find the horizontal asymptotes. Well, by definition, that means I need to have two things that I need to find. I need to find the limit as x approaches positive infinity for this function, and I need to find the limit as x approaches negative infinity for this function. And as I mentioned earlier, if this is a rational function, You should get the same value whether you're going to positive or negative infinity. This, however, is not a rational function because of the square root. If the square root weren't there, it would be a rational function, but that's not what this is. The good news is we're going to start with a similar idea. We're going to divide the numerator and the denominator of this function by something. Now, if it were rational, we would say divide numerator and denominator by x, but that's not going to work out very well, and let me quick show you why. If this were the step that I attempted to take, my denominator would actually work out very well. I could divide x into 3x and divide x into 5 and just write it as 5 over x. This isn't my problem. It's the numerator that's my problem. Can I divide this x into this 2x squared? The answer is absolutely not. Because of the square root, you're not allowed to do that. Remember that a square root is essentially a power. It's a power of 1/2. And according to order of operations, what do you have to take care of first? Exponents or division? Well, it's division. You can't divide into an expression that's being raised to a power, and that's what you would be doing if you divided the x into the 2x squared as it's currently written. So that option is out. What if instead of dividing by x, we instead divided by the square root of x squared? Now, that is not the same thing as x, but as we just discussed in the previous slide, it's darn close. As long as you know in advance that your input is a positive number, the square root of x squared actually is the same thing as x. Now, notice in the numerator, because the 2x squared plus 1 and the x squared share a common exponent, you can instead consider this to be the whole thing underneath the exponent or radical. So now you actually can divide into the 2x squared and the 1, but it's not x that you're dividing in, it's x squared. Now in the denominator, my problem is I now have a square root where I didn't want one, but that's okay. If you know in advance that your input is positive, you can simply replace the square root of x squared with x. So that's actually the approach we're going to take for this one. If we take the limit as x approaches infinity and we divide the numerator and the denominator by the square root of x squared, we then divide our x squared into both terms under the radical, into the 2x squared and the 1. In the denominator, we use the fact that since x is approaching positive infinity, the square root of x squared is exactly the same thing as x. And we divide x into both terms in its numerator, the 3x and the 5. Once we simplify this a bit, notice we end up with a couple of constants, and we end up with a couple of expressions that have a constant in the numerator and something approaching infinity in the denominator. Both of those are going to approach 0, which means that this limit is the square root of 2 over 3. That is the limit as x approaches infinity for this particular function. So don't forget though, we also need to find the limit as x approaches negative infinity. And this one's going to be just a little bit more complicated. We're going to start it off in exactly the same way. We divide the numerator and the denominator by the square root of x squared because we want to be able to simplify the numerator, which contains a square root. The problem is, in order to say the square root of x squared was x, we had to be approaching positive infinity. That's no longer the case. We are now guaranteed that x is not positive, but negative. Well, if x is negative, what was the square root of x squared equal to in that case? Now it's equal to the opposite of x. So that's going to change up the result of our limit. What's going to happen is, when we simplify this, we're going to have to divide negative x into 3x and into 5. When we simplify this, oops, this one's supposed to have a negative infinity in front of it. There we go, still negative. When we simplify this, the 3x over negative x now simplifies to negative 3 instead of positive 3, and the 5 over negative x becomes negative 5 over x, but when paired with the negative in front of it, it becomes a plus. But still, the constants, as you take the limit as x approaches negative infinity, the constants stay constants, and anything that has a constant in the numerator and a variable in the denominator goes to 0. So this time we end up at the square root of 2 over negative 3. So this will be one of those cases where if I look at the horizontal asymptotes for this graph, I have a different horizontal asymptote on the left than I do on the right. On the left, which is where x approaches negative infinity, we know that the horizontal asymptote will be at y equals the square root of 2 divided by negative 3. And on the right, as x approaches positive infinity, the horizontal asymptote will be y equals the square root of 2 over positive 3. Let's take a look at another example. If we try to find the limit as x approaches infinity of the square root of x squared plus 1 minus x. So let's see if we can intuitively determine what happens as x gets infinitely large. As x gets infinitely large, the square root of x squared plus 1 is going to go towards infinity. And so is x. So the problem is we're going to end up with infinity minus infinity. And again, that is an indeterminate form. Specifically, this one's what's referred to as an indeterminate difference. The tendency is to want to say that infinity minus infinity is 0. But the only way that's true is, again, if those infinities are the same. If they're not the same, this isn't 0. So unfortunately, infinity minus infinity is another one of those I don't actually know what the answer is going to be. If this were infinity plus infinity, that's not an indeterminate form anymore. Infinity plus infinity gets infinitely large. So it's the fact that this is a minus. If this particular sign were a positive, we'd be done with this problem. It would be, the answer would be infinity. But that's not what we ended up with. So again, we need to make this look different than it currently looks. Now with the last two examples, what we were able to do was to divide the numerator and the denominator by something that was going to make our function look different. The problem is this one doesn't have an immediately obvious denominator. Or does it? What is in the denominator of every fraction? 1. So we can multiply numerator and denominator by something. Given that this is a radical, for this the technique is to rationalize. You're going to multiply by the square root of x squared plus 1 plus x, numerator and denominator. It looks terrible when you first do it, but believe it or not, this is going to clean up really nicely. We're going to end up looking at the limit as x approaches infinity. In the numerator, you have a FOIL. When you multiply your firsts, you'll have the square root of x squared plus 1 times the square root of x squared plus 1, which is x squared plus 1. Your outsides and your insides are the same product but opposite in sign. So those are going to cancel. And when you multiply the lasts, you're going to get negative x times positive x, which is negative x squared. So notice what's going to happen. In your numerator, all you're going to end up being left with is 1. Well, that's good news, because remember, we love having constants divided by things that are getting infinitely large, which is what's going on down in your denominator. You've now got what we were kind of hoping to have in the original problem. You've got something going to infinity plus something else going to infinity. That's not indeterminate, that's infinitely large. So you have 1 divided by something getting infinitely large. There it is. Automatically, the answer will be 0.